Hello, folks. Welcome to my talk, Building Container Defense and Executable at a Time. My name is Suraj Deshmukh, and yeah, a bit about me. I work as a senior software engineer at Microsoft, and I've been managing this Kubernetes Bangalore meetup for a while now, and you can find me at any of these following places. So yeah, what is today's talk about? So let's talk about the threat model, where an attacker somehow gets access to the container shell, and then from there on they try to do some malicious stuff, like they use containers identity to do something on the cloud provider, or use the containers network to access other stuff, or exploit other pods or machines or whatever. They gain access to the volume in there or secret. So this is the threat model we are targeting at today. And specifically, the attack vector we are trying to see is any attacker, when they get access to the shell, they'll try to download binaries from the internet, where they can use that to do other things. For example, crypto mining is the most popular one these days. So how do we mitigate that, or what's the defense against it? So our defense is disallowing execution of binaries not shipped with the container image. So if we take care of that, here we are assuming like whatever is shipped with a container image is secure, or at least when it was built with an intention of it not being used for with a good intention. Let's see. So what existing solutions we have? We can start a pod or container with read-only file system, but the thing with read-only flag on, when you start a container in KTS, you can still do stuff in /dev partition. Like you can download new files, execute them from there. The other solution is using Scratch-based image. It is the most secure setup, I think, but it is only suitable for apps that have static binaries. Applications that need interpreter won't be able to run in Scratch-based images. They have to be shipped with a bunch of package. So those were existing solutions with their disadvantages. So the new solution that we are proposing is, what if you knew already what is being executed in the container's rootfs? Like whenever something is being invoked, you somehow get a notification or a way of defining whether to allow that execution or not. So if we can do that, then we can design an application that, based on some policies or based on some what a user input, like we can decide what is allowed and what's not. So how do you get those notifications? How do you know what binary is being run? So that's where Fanotify comes in. It's a file system notification framework in Linux. So like from the Fanotify man page, we get this information. Like Fanotify API provides notification and interception of file system events. So this was specifically created for antivirus scanners. We get all kinds of notifications, but specifically we are looking for is the access permission decisions, where if a binary will be executed, will get those notifications. So like how does this look like in action? So here are 4 components that will interact with each other in some way. So obviously there is container runtime, creating containers and managing them, and then the actual container that will be monitoring, the application, as in the our application, the policy enforcer, which runs alongside, and the kernel finally. So obviously the application is continuously looking at what containers are created. So let's say if there is a new container created, we'll poll the container runtime to know that. And once we see that a new container is created, we'll tell kernel that we would like to monitor this particular rootfs. Now this particular the fourth point is not just one step. In actual coding there are two steps here, but for the sake of simplicity I've shown it like it's just one step. So what you get from the kernel is a file descriptor. It's a queue, file descriptor for a queue where you can read events. The events are returned to it, and then we read them and make decisions. So let's say there is a new file binfoo is being executed, at which point the kernel will send the notification to that file descriptor we received earlier, and we get to make the decision whether to allow it or not, depending on whatever our logic is. Until then, that system call, the execution of that binary, is paused. So we have to respond to those events for those binaries to go ahead and execute. So like you can see here, like in this case we have allowed it, but if there is some malicious binary or whatever, we get that notification again, and depending on logic we decide that it should not be allowed execution. So if we send a deny, at which point the executor gets a EPUM or operation not permitted error message. So this is what the simple workflow looks like. So we register for Fanotify events, and then we will get those events. So let's take a deeper look here. So these are the two system calls that we'll make for registering for events. Like Fanotify init creates notification group and returns a file descriptor for the queue, like I said earlier, and the file descriptor is then used in the Fanotify mark system call. So Fanotify mark is used to place a mark or a way of saying this is what you should monitor. So it could be you can place a mark on file system, mount point, directory, file, etc. So it is also used to specify what kind of events you would like to receive, like you want read, write, open, delete, access. There are various others. So yeah, these are the two system calls, and let's see how it looks like with the actual parameters. So here we are saying in the Fanotify init, like we want unlimited queue and unlimited marks. So if you don't specify that, there is upper limit to how many how long the queue can be and how many marks can be stored there. So we are specifying that, and then Fanotify mark, when we call it actual, we are specifying we want to monitor this mount point, and specifically we are looking for open exec permission events. So this is the second parameter is where we are specifying what kind of events we want, and the path. So in our case, we'll monitor proc pid root, and pid being the pid one inside the container. So we'll have a mechanism of figuring out what the pid one inside the container is on the host. It could be mapped to anything else. So yeah, once we do that, we'll start getting those events. So let's look at what the application would look like. There are various designs that we can go forward with. So the first one is something where we'll use diff APIs for verifying something should be allowed or not. Let's look at what diff APIs is first. So yeah, before on the right you see like a typical container base container image with container layer and it being run. So sorry. So what happens is like let's say when the container is created, and in that layer if you create a file slash foobar, it shows up in the end as a final result in the union file system. And if you remove certain file that was shipped with container image, so that won't show up obviously. So union file system takes care of merging all these things that happen at the container runtime level at this level. So that's what we're simulating here. Like I've started a container called example, and here I'm creating the foobar file like you see here, and then removing the user bin touch like you see here. So while this is going on, we can as long as the container exists, we can talk to Docker API and find the diff that it has created from its base image. You can see a foobar file was added and then user bin touch was removed. So in the process, these two directories were also created in the metadata. So in this way, we can see, okay, like a new file foobar is added, which means it's not something that's shipped with the actual container image. And this is what will help us identify, will help us make decision. Let's say an attacker creates this new file and is trying to execute it. And if we see that it's a diff from the base image, we can decide, okay, like this could be malicious and should not be allowed. So yeah, let's see the workflow of this diff model. So like before we saw, we get a notification that binfoo is being executed, at which point we can reach out to the container runtime and see what the diff is. And once we get that, we can make a decision whether that binary binfoo exists in the diff. If it exists in the diff, that means it was modified, and if it does, so we deny that, and we allow it if the binary path doesn't exist in the diff. So like plain simple like that. So this is one model of enforcing it. The second model is where you have like so there are two components to it. We have a runtime verifier like before, but it depends on we getting something called source of truth. Now what this source of truth is, we'll look at it in a bit. So let's say whatever container image that you have is built with like you have all the binaries in there, and your build system gives you extra metadata about those binaries. Let's say your build system is built with secure software supply chain in mind, at which point you can have a list of all the binaries and their hashes. So I mean, it's not necessary, but it is possible that your build system takes care of it. Or the other way to build this source of truth is you can calculate this on the fly before the container starts, after the container has been unpacked on the file system, before PID1 starts obviously. And the third possibility is you can have some REST service running. So every time a container is started, or like it can have a local cache where you just make a API call and then it gives you this list of hashes and binaries. So this becomes your source of truth. So this is what you'll trust as something that was shipped with the container image, and you can rely on this to make your further decision set of verification. So similarly, the way this looks like is you get a event that binfoo is being executed, at which point you calculate the current hash of that binary as it is on the root fs of the container. Like, so at which point So once you calculate the current hash, you can match it against the existing hash that you have from the source of truth. So if the hashes match, that means the binary wasn't changed, and if it doesn't, then obviously the binary was modified. So like this, you can make the decision whether to allow certain binary to execute or not. So yeah, like the two designs have their own pros and cons. Like design one is does not need those pre-computed hashes. It removes the whole logistics of creating them and things like that. But which design two obviously needs to function. Second is design one depends. It depends on the container runtime to provide those diffs. Which design 2 doesn't. It's runtime agnostic. So we can so what this does is like it adds dependency on the runtime to be online, and like without it the design 1 won't function. So but design 2 doesn't care about the uptime of runtimes. It will continue to run. So and that's why like the other thing is almost all runtimes have decoupled the container and container runtime manager by creating like with Docker has done containerd and then containerd shim for each container. So using this diff API kind of introduces the dependency, thus rendering the decoupling useless. So pros and cons. So let's see what policy enforcer app where it can run. Even depending on that, there are pros and cons of it. Like let's say we create a standalone application which runs as daemon using systemd or Kubernetes daemon set or whatever. The pros are like we have flexibility. Especially with Kubernetes daemon set, we have flexibility in policy change enforcement. Like we can create a operator which is backed by CRD, and then users just modify those policies on the go, and then it is enforced accordingly. But the cons are like a single daemon which monitors single daemon on the node which is monitoring all the containers. The problem with it is if it goes down, then like what would be monitoring the containers? So there could be attacks like that taking advantage of that. What are the other timing issues are let's say your enforcing application starts after the containers to be enforced starts. So such issues can happen. The other place to put your code or this enforcing app would be in the containerd shim. So containerd shim runs as a daemon for each container. This is assuming with containerd. So if the code lives there, that means the container like this monitoring code, like it takes birth and dies with the container itself. So we don't have all the problem of late start and all that. And but the problem is inflexibility in policy change enforcement. Like with CRDs, we can enforce that. Containerd shim lives as a binary on the host, and then it's just invoked by containerd. So we have that problem of getting all that policy translated at the host level. And then also there are other issues like since this will be a custom containerd shim, issues with shipping that, having a different installation process and things like that. Anyway, so moving forward. So we talked about what the earlier, before we started looking at this new solution, we talked about what the existing solutions were and how this solution, this new solution adds benefits over them. Like with read-only file system, we saw like /dev was writable, but everything else was not writable. Here, everything is writable, but not executable. So even with /dev or whatever, any partition user writes files to, and then if we are since we are monitoring the whole root container file system, they cannot execute anything. And then on top, and the scratch based image, like we saw, it was only helpful with static applications. So with this solution, even the interpreter based application can be run without being fear of compromised, or even with that baggage, if it is vulnerable and attacker gets access to the shell, they cannot do anything, because we have this application monitoring what binaries are being executed. So yeah, let's look at a demo, a small demo. So here I'm on this node. It's a single node Kubernetes cluster. I wanted also to show you all the containerd logs, what's going on here. Let's start a container, a pod, and let's see. And okay, it's running. Let's say I'm doing a kubectl exec, but let's say an attacker gets access to the shell of this particular pod, and so now that they have access, so what can they do? So they can create a new file, for example, and you can see like there are events going on up there. Okay, these are all the events that are for debugging purposes. I'm showing like the like this particular thing is allowed. Like we ran touch this new file, and then we see that this particular binary was executed, and it says that this was allowed. All right, we can see that this new file accessed here, new file. So let's try to simulate something. Like an attacker tries to remove an existing binary and replace it with something new. So let's say our application depends on this binary, and then it will eventually run shell out and exec this binary. So we are trying, so as an attacker, we are trying to remove that binary and create a new one in its place. So this new binary is created. Let's give it executable permissions. And now if I try to run that, like you can see here, up here, down here I got our operation not permitted. Obviously it wasn't executed. And up here I got a deny message as well, like as a log. So that shows that we have successfully averted this attack, where an attacker, like either they try to replace existing binary or create new one or whatever. It doesn't matter, since our application sees that this is something new that wasn't shipped with the image, we don't allow it. So yeah, that was the small demo. So what are the disadvantages of this whole Fanotify based eventing? First of all, it's a user space program. It could slow down the container application due to the kernel mode, user mode transition. Also, we are calculating, in this particular case, since we are calculating those hashes, it is also slower. But we have seen most of these events, or most of the execution for a long running application, let's say in this case Nginx E1, the events are only generated at the start when the application is booting up or the container is booting up. Once the boot up has been done, it rarely happens that there are events being generated. So also again, like it is not a general thing. It depends on the application as well, how many events or new events it will generate at runtime. But in a typical application, it should not generate more applications. It will only generate them at the boot time. So with this, will only increase the boot up time of the application. The second disadvantage is these events are stored in memory. So if they are not processed, it could lead to memory exhaustion on the node. Although like in our example code, like we saw, we created an unlimited queue with unlimited marks. So yeah, we can limit that. We can we can have different parameters so that the number of events that are stored are less. The third disadvantage is we rely on Fanotify to get events like open exec permission events, but they are generated only when a file is opened using exec CVE or exec CVEat or uselib system calls. So if someone loads the file into memory and then jumps to it directly using memempty system call, then no event will be generated. Fanotify won't know it. Fanotify works at the file system level, so that will be skipped, and then we won't know something like this has happened. So that's possible, but then again we can block this system calls at seccomp level using seccomp profiles designed for these containers. So yeah, we can add security from using that feature of Kubernetes. The fourth point is like it is also possible, let's say if an attacker pipes let's say they do curl some URL and then pipes that script into Python. It is possible and so with Python the events that will be generated will be only for curl and the Python interpreter itself. So the problem is, since both were shipped with the container image, they both will be allowed and we won't know it. So so here the application has to be smarter and figure out like such bypasses are being employed. We can even disallow stdin for Python interpreter or whatever. And the final problem is like we need to be careful as a application designer, like with what events we subscribe to, because it is easy to create deadlocks with Fanotify. Let's say if we subscribe to read events and our enforcer app also is reading files from the container root FS, then it will generate even more events in the process, and it could quickly spiral down into deadlocks. So yeah, these are a bunch of disadvantages of this. But yeah, going forward on the roadmap of what we're working on, we plan on creating fine-grained policies where users can provide some deny list, for example, of let's say some interpreters they don't want to have stdin access and things like that. So yeah, and I think with that, that's the end of my talk. So thanks for attending and listening.